I didn't want to.
Teach us how to control the fixed points.
But
the centric linking
that's
system
right.
from
That's
the
right. Free them.
classification of finite.
That's exactly why I added that comma, because I don't. There are multiple ways to interpret it without a comma. I thank you, Radu, and thanks to Sune for having me here. So as mentioned, huh? Here? Ah, good. Okay. Yeah, so I'm gonna speak about joint work with George Glauberman, and a lot of our aspects of this work is group theoretic, and that's and maybe if you're being generous, maybe representation theoretic. That's the first part of the title, and so. But first, my plan is I want to. In the end result is that we sort of plug into the some reductions, the problem of showing there's a unique centric linking system to each saturated fusion system that were developed by Chermak and then Bob to show that to give a new proof that's augmented by this stuff that doesn't depend on the classification. So the plan for the talk is the first half. I want to sort of motivate that problem, that group theoretic problem, and then for the last half, it'll get more group theoretic. Now, so for my purposes, I sort of want to think about so always the saturated fusion system over a finite P group, and so I want to think about the centric linking system, if we have one, as an extension category of F, or maybe the full subcategory at the level of centric subgroups, and by the center functor. So, and I want to say what that is. So it's a functor. It's a contravariant functor from the orbit category of the fusion system at the level of centric subgroups, which takes two abelian groups, and it's contravariant. So I'm supposed to put that maybe. And it sends an object to its center, and it sends a morphism in the orbit category. So maybe I'll write that. This is a class modulo the inner automorphisms of Q, and that gets sent to, now, taking centralizers is reverses inclusion. So this embeds in the center of the image of P, and then you go by the inverse of phi restricted to this subgroup. So the composite does not depend on the class. Okay. So let me just say a couple of words here. So if you do have a centric linking system, that comes with a functor, and it's a quotient functor. And that's the identity on objects. And on more, I just want to write down the automorphisms. So of an object. And the first one, pi, is a quotient map, and the kernel is, or at least can be identified with the center of P. So you have exact sequences. And maybe better is to view this as an extension, this group here, this automorphism, L automorphism group is an extension of P by outer automorphisms. And so now assume that we don't have L in the picture, and we're trying to at least extend automorphism groups to something that should be the automorphism group in L of a centric subgroup. So now assume sort of have only, and we want to put a finite group here, an extension of P by a group acting as outer automorphisms, and of course there's a obstruction theory that tells us when we can do this. So there's an obstruction to existence and uniqueness of gamma in third cohomology of the outer automorphism group with coefficients in the center, and then uniqueness in H2. But in this particular case, we know what we want the extension to be on the level of P groups because, or at least if P is fully normalized, at least, then the normalizer in S of P is should be a CELO subgroup of whatever group we put there. And so since that is known, but so we have an obstruction here, and it vanishes on the level of upon restriction to this group, or at least out S of P, and so it vanishes. And similarly, the particular obstruction H2 vanishes. So we know what this should be, and this, of course, is turns out to be the model for the constrained system in F of P. Now, and also ought L of P. So the theorem of Brodo, Levy, and Oliver in 2003 is that there are obstructions to existence and uniqueness of a centric linking system given F in and the cohomology of third cohomology and second cohomology of the center functor. Okay, so I can give you sort of an outline of sort of where our work fits into this trying to prove existence and uniqueness. So maybe I'll start over here. So we want to show there's a unique centric linking system. And it's actually expected that all these higher limits of the center functor would vanish. And so it should be acyclic if P is odd. I may not have enough room here. And in all above degree 2, second, yeah, so lim k should vanish for all k greater than or equal to 2. If p is equal to 2. And this, I think, this is what was proved in Bob's original papers on the Martino-Pretty conjecture, when F is the fusion system of a finite group. And I'll hope to say a few words about the Chermak filtration. It's a way, this gives a way to break up the center functor into subquotients in a way that makes it possible to prove that the higher limits of those functors vanish. So this allows one to reduce to the problem to showing that lim 1, not all higher limits, just lim 1 of a certain one of these subquotients, but now where the fusion system is replaced by the fusion system of a finite group gamma, and in fact a constrained group gamma. I'll say what that is in a minute. And then where the group theory comes in is in helping to show that in this residual case, lim 1 vanishes. So I have to say, there's a lot of stuff here. It also gives some information at the prime 2, but more work is needed after that I probably won't get to say today at the prime 2 after this is sort of done. Okay, let's see. So I need to say what gamma is. Well, you can maybe guess, but I do want to give a definition. Finite group gamma is P constrained. For the purposes of this talk, usually it's a little bit more general than this, but it's P constrained if there's a normal P subgroup of gamma Y containing its centralizer in gamma. So the way you study such a group is that you you look at the center of Y. So the center of Y, quotient out by the things that act trivially on the center of Y. That's usually a proper subgroup, and this acts faithfully. So in this way, you get sort of toward representation theory, because this is an abelian P group. So I'm generally going to call this V and this G. Okay, and well, Thomson back in the 1960s, he studied. He studied P-constrained groups very deeply, and what he showed was that in a lot of situations you can factor this group as a product of two local subgroups, normalizers of P subgroups. Actually, one is the centralizer of the center of Y, and the other one's the normalizer of an important characteristic subgroup of a CELO group called the Thomson subgroup. But anyway, so in a lot of cases you can factor that group, except when you can't, and obstructions to having what's now called Thomson factorization is is the existence of what are called offenders in G on V. So let's say, so I'm going to keep this notation. G could be any finite group with a faithful action on an abelian P group. So A in G is an offender on V if, well, an abelian, these are always abelian P subgroup is an offender on V if the size of its fixed points on V are large relative to its size. That's kind of how I think about it. And hopefully this is not a problem. This is really fixed points. So for a group theorist, it's centralizer, because we secretly think we're in a semi-direct product all the time. This is bigger than the size of V. Okay, so let me give some examples of this. Oh, there's something, it occurred to me there's something that I forgot to say over here. I want to say that there's a version of this work that was done by Remy for fusion systems over discrete p-toroidal groups. So I think those are called p-local compact groups, yeah, for p-local compact groups. So infinite versions of fusion systems, yeah. So, yeah, example. Let's see. So, so let's assume I just want to think of V being elementary abelian. So in other words, it's a module for G over the prime field. And because it's easier to say a couple things that way. But anyway, any group generated by a transvection. So let me call that A transvection. So in other words, the commutator, I'm thinking of this being in the endomorphism group of ring of V. This is contained in the fixed points, and this is of codimension 1. So elementary matrices, say. And then just maybe let me point out rectangular. So if I take G to be SL in P and A to be some rectangular subgroup of unipotent matrices, say something like this. That's a unipotent radical of a maximal parabolic, and it's an offender because, well, let's see, CV of A, what's that? That's the size of the common one eigenspace for all these matrices, which is two-dimensional. So that's P squared, and this A itself has size. What? Oh, what is the module? I mean, I just want to take the natural one. I guess this is 5, isn't it? N is 5. And A has order P to the, looks like 6. 6, and V has order P to the 5th. So the product here is actually quite a bit larger. And because it will become important later, I want to mention the special case where, for example, you have the symmetric group and you're acting on a module over the F2, the permutation module over the field with two elements. Then a transposition will be a transvection, say 1, 2, would be a transvection. Okay. So in the next 10 minutes, I'll try to say some remarks about the Chermak filtration. Okay. So the idea, right? A lot of what I say is you know, about these computing limits of the center functor, you know, is appeared, you know, or go back to Bob's papers and on the Martino-Purdy conjecture, and maybe earlier, but then I'll try to point out what's special about the Chermak filtration. So the idea is you're going to filter. So the general idea is you want to filter by breaking up the subgroups, the centric subgroups into pieces. Maybe, you know, maybe it's best if I try to draw a picture. So when you, so I'm going to maybe draw the, I'm thinking of the subgroup lattice of the, given by the F-centric subgroups. And anytime you can break this up into, you know, partition this set into what are called intervals. So this is an interval, F invariant interval. In other words, it's closed under F conjugation, so F invariant interval. It's an interval in the subgroup lattice. So, and it also contains it's F invariant. Everything closed under conjugation and F. When you have such a thing, you can make a what's in general a subquotient functor. Where you just violently truncate outside of this interval. So you just say, well, it's going to be center of P if P is in R, and it's going to be 0 or 1, depending on whether you're additive or multiplicative, if not. So in general, this is a subquotient. And if you can show that if you can partition properly, and you can show that all of these functors have vanishing limits, then the original center functor does as well. Now, for most nice ways of intervals, let's see, is there something I make sure there's not? You can actually express the limits of this subquotient functor in terms of the limits of a similar functor, but over the orbit category of a group. And namely, so if you take a minimal subgroup of this interval, and you look at all the subgroups in between it and its normalizer, which will generally be bigger, stick outside of R. Well, corresponding to y, we have our old friend gamma, which is sort of like the normalizer of y. And in good cases, most cases, you can express the limits of this truncated functor in terms of the this is isomorphic to now over the orbit category of gamma, p orbit category of gamma. And gamma is a is the fusion. It's a group. So basically, we're going to reduce to working within a constrained group gamma. By the way, p-constrained groups are just models of local subsystems. There's nothing, they're exactly the same. So now we work in gamma. And by R here, I don't mean actually the full thing. I mean the elements of R that are containing Y and are in the normalizer in S of Y. So then you can look at what's left in the subgroups of the normalizer in S of Y containing Y. So working in gamma, you have an exact sequence. This should be gamma. Of functors. And this gives you long exact sequences on a higher limit. So I just want to point out part of it. So at the level of just lim 0, what you get, because we're in a constrained group, we have the center of Y sitting down here, containing all of our centers above Y. Inverse limit is the fixed points of gamma on the center of Y. And over here, we have only centers from subgroups in Q. And what you end up getting, just from the definition of the inverse limit, you get the fixed points of a subset of gamma on the center of Y, where this subset is the set of group elements with the property that conjugates some member of script Q into script Q. So I hope my scripts are distinguishable from my Roman letters for some Q in Q.
If you can reduce this higher limit computation to finite group gamma, wouldn't you just say, because we know the existence of vacancies?
Yeah, there's an important issue here. This is not this functor. Where is it? Yeah, maybe this one. This functor is not. This is not the center functor of gamma, and in general will not have the same limits as the center functor of gamma, because now because it's not going to it's going to be 0 above the interval r, where r intersects gamma. Yeah. Mm-hmm. But that doesn't necessarily get you very far. But what you can say is that the difference. Well, this is yeah. If you see up there, I'm claiming that's what we. It would suffice to show this for this is 0 for p odd, and that comes from properties of the Chermak filtration that I haven't said yet. But the reason why this is 0 is because this functor turns out to be a Mackey functor, or the contravariant part of a Mackey functor for the orbit category of for the orbit category of gamma, or at least the quotient of gamma by y. So it has vanishing limits. This is why this is 0 here, and also if you look at the next line, what you'll have is that lim1 z q is lim2 z r. Okay, well, I've said too much. I've said more than I wanted to say, and I still haven't told you what is great about the Chermak filtration. The important thing is so the special things are, first of all, there's a symmetry. So these are built, the intervals are built out of the, so the intervals are built out of the Thompson subgroup, based on the Thompson subgroup. Of the subgroups. I'm afraid I'm going to have to, I'm not going to say it, but there's a connection with, I did say it earlier, and there's a connection with offenders. There's a symmetry, a sort of symmetry that lets you do some dimension reduction arguments to reduce to lim1 and lim2, correspondingly when p is odd or p equals 2. And lastly, these intervals are very explicit, or at least when considered inside gamma. It's the set of subgroups of G set of subgroups of normalizer in S of y containing y, whose image is in G, contain no non-trivial offenders. V, center of Y. And script Q are the ones that do, whose images in G do. Contain offenders on. So this is what this is very important. And the reason why it's very important, I'll say, did I? Yeah, okay. Is that what that means is, in gamma, there are subgroups in Q whose images in G have special action on V, and in particular, quadratic action. So I define an offender here. So an abelian, so a subgroup A acts quadratically on V if in the endomorphism ring 1 minus A times 1 minus B times V, this annihilates V. In other words, the centralizer of the commutator of B on V is contained in the centralizer of A for all. So this is in the endomorphism ring for all A, B, and A. And what Thomson showed, the most important thing about offenders, Thomson, 1964 maybe, showed that each offender, so non-trivial offender, contains an offender, non-trivial offender, acting quadratically on V. Okay. So that's what we need. Now I'm going to draw your attention back to this exact sequence here, and move on to the group theoretic part of the talk. Any questions so far? This is the first part of the long exact sequence in, yeah. So that's the first part of it, and then here's a bit from the, I guess the next one. The next one is this, and the next one is the connecting map, taking you here, and that's an isomorphism. Huh?
Why is the first C?
Oh, this one. Because, well, actually, I cheated a little bit. In this picture, if if R if R is the entire set of subgroups, if R contains the, this doesn't happen in the Chirmac filtration that I know of, but if R is the if the whole set of subgroups between Y and NS of Y is contained in the interval R, then actually this won't be 0. But if just a little bit is not, then what you have is the functor here is 0 up on at the top on NS of Y, because at least the functor corresponding to R. And so you have the value here, value 0 at the top, and so since this supports a morphism from every centric subgroup, you can't have a stable element being non-zero. That's why lem 0 is there. Yeah. Okay. So we're interested in showing this vanishes so that these are the same here. One thing I should, I guess, point out before we go on is that this is the set of subgroups conjugating some member of script Q back into Q. So in particular, if you have an object, in particular, if you have an object Q in this collection, then the normalizer in gamma of Q will be contained in the set because it conjugates Q to itself, right? So if you could show that the normalizer of some member of script Q has the same fixed points on the module as does gamma, then you've shown this is an isomorphism and that's 0. So that's the problem. So for simplicity, I want to take a group acting faithfully on a. For simplicity, I'm going to take it to be elementary abelian. So this is an FPG module, just for simplicity. Nothing much is lost. The problem is to find a p-local subgroup. Let's call it H. It's going to be a subgroup of P subgroup J with same fixed points as on the module B has G. And let me give some examples, and all of these examples we'll have that the group acting has no fixed points, okay? And so we just need to find a p-local subgroup with that property as well. So let me take p odd and take G to be SL2P. And I want to take V to be just the natural module. Now you can see a CLO subgroup as maybe upper triangular matrices with ones on the diagonal. That's of order P. The normalizer of it is a Borel subgroup. And we take that for H. because the diagonal, the split torus has no fixed points on the module. You see why I took p odd now. Because now for p equals 2, same example. S has order 2, and it has non-trivial fixed points, and it's equal to its normalizer. So, I mean, what we're talking about is SL22, which is S3. And in this case, H doesn't exist. So you can't solve this problem for it's a sort of like it's a very small, I mean, we want to try to solve this in as many cases as possible, and this is very discouraging at the prime 2. If you, on the other hand, if you go up one dimension, then you can again take S to be upper triangular. This is dihedral of order 8, and let's see, no fixed points. So we need a two local subgroup that has no fixed points. If you take J to be this guy, that's elementary. That's a 4 group. That's elementary of rank 2, and what's the normalizer? It's this parabolic over here, and you notice it doesn't have any common one eigenspace. These matrices don't have any common one eigenspace, so you can actually solve the problem here. You just take H to be that. Of course, if you took the other parabolic, then fixing a point, then it wouldn't work. But this works. So maybe not all is lost. And let me just mention So George solved this, gave a sufficient condition for you to be able to solve this problem at odd primes back in 71 or thereabouts. So let me state that theorem. So the point is here is quadratic action, at least when p is odd. So let G act faithfully on V. The same setup as before. Elementary abelian, doesn't matter. It's actually much more general than this, but if G has an element A acting quadratically, so what does that mean? That just means that it has quadratic minimum polynomial on V. So acting quadratically, then you can solve this problem. And there's a P subgroup J with normalizer J having the same fixed points as the large group G. And how do you get this? You take a CELO subgroup of G that contains A, and then you let J be the set of conjugates, G conjugates of A in S. So in other words, what's typically sometimes called the weak closure of the element in S. And this does the job. Mm-hmm. Oh, yes. Please. Please, yes. It's as you can see, this is false with the example that we took here, because every involution has quadratic minimum polynomial on an elementary abelian group. Yeah. So by the way, from the properties of the Chermak filtration, remember, we're interested in finding some element of the script Q whose normalizer has the same fixed points on the center of that constraint of Y in the notation before. But and those elements of script Q have a certain action. They have offenders. They have offenders on the center of Y. And so by Thomson's theorem, they have abelian, they have quadratic offenders. So they do have quadratic elements. And what this means is that this is enough in order to finish the proof for odd primes of existence and uniqueness. This is enough. So the question is, what do you do for the prime 2? And let me just go ahead and state maybe what could be viewed as the corresponding result in our paper. And it says that I'm not supposed to abbreviate his, am I? He's always GG. So okay. So let's now we take the prime 2, okay? And same setup. G acts faithfully on for simplicity, you can assume elementary abelian, because I want to. And suppose G has an offender on V. That's sort of the setup we're presented with in existence and uniqueness from the Chermak filtration. Okay, then either we can solve this problem there's a 2 subgroup J with what we want. And in this and it does correspond directly. So in these particular cases, for the kind of constrained groups that give you these conditions, this lim1 will vanish. Lim1 of the residual functor on the orbit category of the constrained group gamma will vanish, and so now look back at the example with S3 there. Each minimal offender under inclusion is of order 2. And order 2. Because I've assumed that V's elementary abelian, an offender of order 2 is precisely a transvection, or at least is generated by a transvection, is a transvection. is generated by a transvection. And then we can also know information about how this transvection is embedded in the group. Moreover, let's call this, what do I want? Do I want maybe A? Okay, moreover, if you fix a CELO subgroup, no, the other way around, containing A, then A centralizes. No, sorry. Then A is contained in an S3. So it's one of the. It's a transvection. It's in a symmetric 3, sort of like up there, and this S3 centralizes every other minimal offender in S. Well, it's a little complicated, but maybe I can give an example. So these kinds of transvections we call solitary offenders. So then it is solitary by definition. So let me give an example. I'll give a quick example, and then I'll say a couple words to finish. So the example that I like is G is symmetric 7, and V is the permutation module. Very simple. How do you locate a CELO 2 subgroup of this? If you take the standard set on which this acts, 7 letters, and you partition it like this, you can choose a CELO subgroup to preserve this partition. And so in particular, it's got transpositions there in it. And each one of these is, and so this is sort of in S. Each one of these is a transvection on V, and each one of them is solitary, or the group they generate of order 2 is solitary. You can look and see, say for example 5, 6. Think of this as being A, and take the symmetric 3 to be the one that's moving 5, 6, 7. And that's a symmetric 3 containing A and centralizing all. In fact, these are the only these are the only transvections in the CELO 2 subgroup. So and this symmetric 3 is centralizing all the other ones. Yeah. So let me just state this. Last thing. And by the way, control of fixed points you can't solve. You can't find a 2 local. here that has the same fixed points as G does. They'll always be fixing this extra thing. No, that's not quite right. But so anyway, so if in addition, suppose we're in the bad case, case 2. So assume the setup of this theorem. Assume we're in case 2, and G is generated by its solitary offenders. And G has no normal, no non-trivial normal 2 subgroup. Then, and this is the result that allows us to avoid the classification. This is really the one. This is really the one. Then G is a product of symmetric groups, direct product of symmetric groups of odd degree, and V up there, V is a well, up to fixed points is a direct sum of natural modules for the symmetric group. So natural means not quite the permutation module, but modulo fixed points, yeah, of natural modules. And just to finish, in this, the way the classification is used in the original proof of Andy's is that, and Bob's is that you need a full classification of all the groups that are generated by offenders. And that requires, or at least simple groups, the simple groups that have a module, and on which they have offenders, and they're generated by those. In this theorem, we are able to get by with McLaughlin's classification of groups generated by transvections, which is I think about a 10-page paper. So it's well, thank you. Thanks. That's it.